Welcome to this explainer. Look, if you're currently studying advanced math, you already know the drill. You sit down for what feels like a 3-hour marathon session, just staring at a literal mountain of equations. You're told to memorize rule after rule after rule, and before you know it, the whole topic of differentiation just starts to feel incredibly rigid, mechanical, like you're just a calculator. But today, we are going to break that illusion. We're going to uncover the beautiful, dynamic reality that's actually hiding right beneath all those formulas. Let's jump in.
So ask yourself, why does learning differentiation feel like operating some confusing, clunky machine? If you've ever felt completely overwhelmed while staring at a massive, 60-page resource pack full of calculus drills, you are absolutely not alone. It's a super common trap. And to figure out why we all fall into it so easily, we need to take a hard look at how this stuff is actually introduced in the classroom. Because, well, here's the trap. The syllabus basically hits you with a rapid-fire barrage of rules. First, it's the power rule. Just bring down the exponent. Easy enough, right? But then, bam, you're juggling the chain rule for functions inside of functions, which, let's be real, has traumatized the best of us. Then come the product and quotient rules, L'Hopital's rule, implicit differentiation, and eventually the whole shebang with Maclaurin's series. It makes the entire subject feel like a cold, calculating engine. You're just taking a function, shoving it into this machine, and turning the crank to get an output without ever really knowing what the machine is actually doing on the inside. Actually, there's a brilliant quote from Revision Dojo that hits the nail right on the head here. The mechanical feeling comes from learning techniques before meaning, and that is exactly our core diagnosis. The educational system forces you to memorize the machinery way before it ever bothers to teach you what the machine is for. The how is hammered in so heavily that the why just gets completely lost in a sea of algebra.
Think about the contrast for a second. On one side, we have the mechanical procedure, the rigid illusion of just bringing down the power and subtracting 1. If you have x squared, bring down the 2, subtract 1, you get 2x, boom. But that's just a mechanical trick. On the exact opposite side, we have the conceptual meaning, the dynamic reality of describing a curve's actual physical movement. Remember, mathematics is ultimately a language. It's used to describe the living, breathing, real world. It's not just a set of arbitrary parlor tricks.
Section 1. Finding the true meaning. Rebuilding the concept visually.
Okay, so what is a derivative, really? At its absolute core, it's simply the slope of a curve that is constantly changing, and we find it by zooming in infinitely close to a specific point. Unlike a straight line, which obviously has the exact same slope everywhere, a curve's slope changes at every single microscopic point along its path. So to find the slope at one specific spot, we have to draw a tangent line. Picture a perfectly straight line that just barely kisses the curve at that exact coordinate. If you were to zoom in infinitely close to that tiny point, the curve and that straight tangent line would actually look completely parallel. They'd basically overlap.
But how do I actually find that perfect tangent line mathematically? Well, we can build it visually, step by step. Step 1. Draw a curve and plot the exact point you care about. Then plot a second point just a little further down the curve. Step 2. Draw a right triangle between those 2 points. You calculate the rise over the run to estimate the slope. Simple geometry, right? But the straight line you just drew doesn't quite match the curve. It's just an approximation. So we need step 3. This is where the magic happens. You simply shrink the base of that right triangle. You drag that second point closer and closer to the first one until the distance between them, the base of your triangle, is essentially 0. When you visualize it like that terrifying algebraic limit definition from your textbook just becomes a really simple, elegant story of a shrinking triangle.
Section 2. The power of limits. Zooming into infinity.
Now, this entire zooming in process, it relies completely on the magic of limits. Limits formalize exactly what happens when we approach a destination that's technically undefined. Imagine you and your friend are driving to school. You live twice as far away, so you drive twice as fast. Makes sense. At any given moment on the journey, the ratio of your distance to their distance is exactly 2. But what happens at the exact instant you both pull into the school parking lot? Both of your distances to the school are now 0. Normal math throws its hands up and says 0 divided by 0 is undefined. Limits, however, swoop in and allow us to look at your specific rates of change as you approach that undefined point, uncovering that the true mathematical ratio is still, beautifully, 2.
Section 3. Real rates of change. Grounding math in reality.
Let's bring this right back to the real world. A rate of change is just how fast a thing is changing at one particular instant. Imagine you're in a car, actively accelerating down the highway. Your speed is constantly changing. You're going faster and faster. But if you were to magically freeze time for a single millisecond and look down at your car's speedometer, that exact instantaneous reading, that is your derivative. It's the precise rate of change of your position at that frozen moment in time. Literally, that is all you're calculating when you use those mechanical rules.
And this real-world logic goes even deeper. If we take the second derivative, which, just means taking the derivative of our first derivative, we find something called concavity. This describes the actual physical curvature of a function. And you can picture it so simply. Just imagine the curve catching rainwater. If the curve bends upwards, like a bowl, it forms a little pool that catches the rain. That's concave up. It means we have a positive second derivative. But if the curve bends downwards, it spills all the water out. That's concave down, meaning a negative second derivative. Oh, and the exact moment the curve flips from catching water to spilling it, that's an inflection point. So even the second derivative, which sounds like incredibly abstract high-level math jargon, is literally just describing the physical shape of a bowl.
Here's the secret. Curriculum boards like IB actually want you to understand this true meaning. They don't just want the machinery. The exams aren't ultimately designed to see if you can perform rapid-fire algebraic gymnastics. They're designed to test if you genuinely grasp this living, breathing language of nature. When they hit you with optimization questions or crazy-related rates problems on an exam, they want you to see the real-world connections. They are practically begging you to look past the blind, mechanical application of the chain rule.
So as we wrap up this explainer, I really want to leave you with a final thought to chew on. We've just unmasked differentiation, right? We took it from this cold, unfeeling machine and turned it back into dynamic, visual geometry. So as you continue your studies, ask yourself, what other elegant geometry is hiding right now behind the rest of the textbook formulas you've been forced to memorize? What other beautiful realities are just waiting to be uncovered once you finally look past the mechanical illusions? Keep looking for the meaning. Stay curious. I promise you, the math will come alive. Thanks for hanging out with me today.